So, let us begin with a quick recap. We are at some kind of a momentous occasion in the codes. We introduced turbo codes, okay, and this is the very famous picture. Okay, so the picture was a very typical situation with turbo codes. You have a rate half convolutional code, okay, and the message goes in here, and then there is a, what is this block? Interleaver, and then once again there is a rate half convolutional code. Here you keep both the systematic version and the parity, here you keep only the parity. Okay, so that is the way we are viewing it. Okay, so maybe you want to terminate it. I might have okay, so I might decide to terminate the first one, in which case you would get the first parity sequence. Okay, if you are terminating the second convolutional encoder also, then you will need some additional bits that will have to be added to this. Okay, so if you do not add it, then you are not terminating the next one. Okay. So here you would have again the second parity, which is let us say P20 all the way to P2k plus 1 if you want. Okay, so these are, this termination is not a big deal. I mean, it is not something that you have to take care of, but it does not change the performance as significantly as long as you terminate at least one. Okay, so it is very typical to terminate the first one and not terminate the second one, okay, and then you are okay. Okay, so nominally this is a rate 1/3 turbo code. Okay, of course, if you account for the terminating bits, there will be slight reduction in the rate, okay, but it is okay, 1/3 is fine, and usually k will have to be large. It has to be at least 50, 100 or something before meaningful results can be obtained. Okay, so 50, 100 is typical. So in that case, the termination is not a big deal. Okay, so once again, to get higher rate codes like rate half and all that, you would puncture. Okay, and there are puncturing patterns that are possible depending on what rate you want. For rate half, there is a standard puncturing pattern where you keep all the odd numbered bits from one parity and keep all the even numbered bits in the other parity. Okay, so that is something that is a bit more standard in rate half. Okay. Any questions on this general structure? Okay. So the crucial point is both these guys can be the same code, but they will have to be recursive systematic convolutional encoders. Okay. All right. So once you make them recursive systematic convolutional encoders and you put a random interleaver here, and when k is large, the number of low weight code words go down significantly. Okay, so at least that you can easily find go down very sharply. Okay, so because of the interleaver changing some things. Yes. Yeah, you could have it different, but what people have found in practice after so many years of research is that you can keep it as the same code and you do not lose much in performance. All right. Any other question?
So if you just have two RSA encoders and remove the interleaver,
this will not work. Okay, so the question was, can you remove the interleaver and simply do this concatenation? Okay,
no, with two different RSA encoders.
Two different also, it does not work that easily without the interleaver. Okay, so it's easy to find low weight code words if you don't have the interleaver. Okay, so the interleaver is something which adds a non-trivial thing to it. So, the question was, if you put two different RSC encoders, your denominator polynomial is different in both, okay. Then what happens, you will have different things, but then you can always find the LCM of those two, then that leads you to some very simple formula for finding very periodic repetitions will happen, okay. So, you do not get much advantage, but on the other hand, if you do a random interleaver, then it really kills any symmetry in such kind of a situation, okay. So, that is the structure. Like I said, the encoder is motivated in a more or less ad hoc way, I mean, think of how you are getting rid of some low weight code words, and you do not really do anything more beyond that. It is tough to motivate it in a very rigorous way, okay. The most important thing for any error control code is the BER versus SNR curve, okay. So, if it goes very close to capacity and if it is giving you good performance, you are happy, okay. So, that is the main selling point for turbo codes. They have a very good decoder which works well, okay. So, that is what we have to discuss next, okay. Everybody is happy with the encoder as such, it is clear. So, there are as many variations on these encoders as there are probably researchers in this field, I mean, people have different variations. One very popular variation is the serial concatenation, okay. What would the serial concatenation look like? You would have an outer convolutional code, an interleaver, and then an inner convolutional code. That is also supposed to be pretty good, and there are properties for that also that people study, and what you do once, you can do multiple times, right. So, you can put one more interleaver and put one more convolutional code, you get more random behavior, right. So, you can keep doing this and change this structure as long as you keep the main mantra in mind. What is that mantra? There should be some random looking interleaver to make sure that you cannot find low weight code words very easily, okay. So, as long as you do that, you will keep getting additional structures, okay. So, of course, the decoder is important, you should make sure that the decoder also extends in a similar way, okay. When I discuss the decoder, that will be a little bit more clear, okay. So, let's maybe see one more example maybe from the standards, this time from the 3GPP standard, okay. So, this is something I remember from memory, hopefully I am right, I will not make a mistake here. So, the G of D they use for the convolutional code is something like 1 and then I think 1 plus D power 3 by 1 plus D squared plus D power 3, okay. So, this is the G of D for rate half recursive systematic convolutional code, okay. Okay, so how many states does this encoder have? 8 state, okay. So, it is an 8 state encoder, okay. I believe in 3GPP you terminate both the encoders, okay. So, there is some additional bits that you send to terminate both encoders after the interleaving, and the interleaver, okay. So, usually in standards they have to specify different block lengths, your block length is not fixed, okay. So, your K is not fixed, K is usually can start at 50 or something, I think 50 or maybe 60, then keeps on going to 100, 200, 300, etc. so on all the way. I think the largest block length they have for this in the 3GPP standard is some 1152 or something like that, okay. So, K will go from some let me say 100, okay, this is only a rough number, okay, to I believe 1152, okay. So, the mother code is the rate 1/3 code, right. The rate 1/3 code is the mother code with this as the component code, and the only thing missing is the interleaver, okay. The interleaver in the 3GPP standard, or maybe even in other standards they use this interleaver, it is what is known as a quadratic permutation polynomial interleaver, QPP interleaver, okay. It is popular for various reasons. I will simply provide a description, but okay. So, basically they will define pi of I to be some f1 I plus some f2 I squared modulo k. Okay. For each k you define a suitable f1 and f2, and then to get the permuted position corresponding to position I is the original unpermuted position 0 1 to k minus 1. To find the position of I after permutation, what do you have to do? You have to evaluate pi of I goes to pi of I, and pi of I is f1 I plus f2 I squared mod k. Okay, so this is called a quadratic permutation polynomial for obvious reasons. Okay, it's quadratic, and you need some conditions on f1, f2 and k to make sure that it's a proper permutation. Okay, that those things are quite standard, you can do that. Okay, so it's appealing for various reasons. What are the various reasons you can think for which this interleaver is appealing? Okay, so remember, the main selling point for convolutional codes is that the encoder is simple. Okay, so it's really dirt simple, very cheap. Okay, now if you look at this picture, which is the most complicated part to implement in this picture? The interleaver, right? So everything else is trivial. It's just 3D flip flops. You don't even care about it. So the interleaver, you can't expect a memory of 1152 or something, a huge memory, and then randomly access it, pull it out. It's going to increase your power spent. Okay, so this one is particularly simple, right? So you can compute the position. You don't have to necessarily store it somewhere. Okay, so you only have to store the f1s and f2s. You don't have to store as many as the entire array. You don't have to store. Okay, so you store f1, f2 and compute it on the fly and figure out what position it goes to. Okay, so that is something that can be done without too much effort. So that's one reason why it's popular. There is another more significant reason why it's popular. I'll address that later when we talk about the decoding. Okay, so right now this is at least complexity is very less. Okay, and also the other condition is it should be random enough. It should not be very regular, right? So this quadratic function makes sure that the permutation looks random enough. It will not be a very simple permutation. Okay, if I give you the permutation, you will never be able to guess that it comes from a quadratic function. Okay, so it's just it looks random enough, and it satisfies that constraint also. So it's a pretty popular thing that's used. Is there a question?
Does this have any connection with hashing?
Hashing, okay. So I don't know about hashing. No, I'm not familiar with any connection. Maybe there is. But this is not really hashing. This is one-to-one mapping. No, I mean, it's a proper permutation. Hashing, usually you take something very large and then put it into a small set, right? So this is a one-to-one map. So interleaving is not like hashing that way. Okay, but the method might have some similarity. In hashing, they do a linear function usually. Quadratic also maybe is popular, but here you make sure that the coefficients are chosen so that no such hashing effect happens, as in you don't reduce the size significantly, keep the size the same. So this should be an invertible map. Okay. All right. So this is just for information, and then let's move on to the famous turbo decoder. Okay, so turbo decoder today is both a particular decoder for the turbo code and also a concept. Okay, so in general there is this turbo principle which is used in this concept of a turbo decoder, and it can be used for anything other than codes also. Okay, anytime you have a concatenation of two trellises, okay, or not necessarily trellises, two structured entities. Okay, so you can decode one and then use the turbo principle, go to the other and then come back using the turbo principle, etc., etc. So it's basically like a message passing type of decoder, but you go back and forth, and that's the turbo principle idea. Okay, so apparently in cars, I don't know how many of you know about mechanical engineering. I don't know, it's been a long time. So in cars there is this turbo drive, right? So it's called turbo for that reason. There is something like energy goes from one out and then comes back and something. I don't know. Does anyone know more about this? No, nobody knows. Okay, that's supposed to be the inspiration for the name. That's where the name comes from. The turbo is basically something like there is a cycle or something. They use it in some way to make it better. Okay, but today this word turbo basically means in anything you give it a turbo boost, so to speak, right? So even in processors you have this turbo concept. So anything which seems to do better than it should is called turbo. Okay, so that's the idea in this word today. I mean, it has a more colloquial use, but in the main principle comes because you do it in cycles over and over again, and you gain some improvement, small improvements, and eventually they add up to something very big. okay, that is the idea, the turbo principle. Okay. So in general, what do we have in the, so okay, so let us look at the encoder once again and then see what we can say about the received word. Okay. So you have a code word, so let us say we are using the rate 1/3 turbo code, okay, the typical code. I will describe the decoder for this code, and once again the extensions to other codes are easy. Okay. So if you have this, then the transmitted code word, which I think we call V, is going to be something like U0, P10, P20, U1, P11, P21, so on till U. I will stop with K. Okay. So I will not K minus 1, I will not worry about the termination, but when there is some termination going on, depending on whether you are in the first code or the other code, there is some termination going on. So I will keep it at K minus 1 just for just to keep the notation simple and not worry about too many other things. Okay. So there are some other termination stuff, and that is your code word. Okay. And this goes through BPSK, and you will get your what have I been calling this thing, maybe Y. Okay. So Y, this is going to be Y0. Okay. So now we need a slightly better notation. So what I am going to do is, so I will put a 1 here to indicate that it corresponds to the first parity. Okay. So and then 2 here to indicate that it corresponds to the second parity. Okay. So keep everything else the same, just make the replace it as Y. Okay. So Y1 1, Y2 1, so on all the way to Y K minus 1, Y1 K minus 1, Y2 K minus 1, and you also have the termination stuff depending on how you have terminated. Okay. So now this is my received word, and I have to do a decoding. Okay. I know that convolutional codes have very good decoders, they have very good soft input, soft output decoders like the BCJR algorithm and all that. Okay. So I am going to use that. Okay. But then the entire code word is not a code word of the convolutional code, okay, not a single convolutional code, right. So it is a code, it is a concatenated version from 2 different convolutional codes. However, from the code word I can extract a part of it which will definitely be a code word of one of the convolutional codes. Okay. In fact, there are 2 different convolutional code words that are subsets, so to speak, of this code word. What are the 2 convolutional code words? U along with P1, that forms a code word of the convolutional code on the top. U along with P2 forms a code word of the convolutional code at the bottom. Okay. So I can run 2 different convolutional decoders, maybe Viterbi I might want to run, or maybe I want to run BCJR. Okay. So I can run 2 different convolutional decoders on this received word and get estimates of each of these bits, okay, estimates of U at least. Okay. I am interested only in estimates of U, right. Remember, the convolutional decoder for BCJR gives you only the LLRs for U. You can also find LLRs for the parity, but usually nobody does that. Okay. So you only find LLRs for U. Okay. So I will get 2 different LLRs for U. Okay. So anytime you have more than one LLR for your message bits, what do? You try to pass that message from one to the other and try and repeat the decoding to make sure that you can get more benefit out of it. The only thing you have to make sure when you do the passing is you should pass extrinsic information, you should not pass anything that is intrinsic. Okay. So that is a little bit more tricky to figure out in the convolutional code. What is extrinsic and what is intrinsic is a little bit more tricky. Once you figure that out, you can do some message passing iterative decoding. Okay. So you have 2 different component decoders, one for one part of the code word, another for another part of the code word. You decode it independently and then pass extrinsic information from one to the other and try and improve the other decoder. Okay. So in principle it is still message passing. Okay. So this turbo principle is actually a message passing principle. Okay. And there are parallels between this and what we did with LDPC decoders also, right. except that in the LDPC decoder, what are the component decoders? Okay, you think of the Tanner graph, the component decoders are the check nodes. Okay, what code are they decoding? Okay, the check node is doing something, right? The check node is trying to decode which code?
Just
think about it. It's decoding a sub code, right? So see, check node is connected to a subset of the bits, and those bits satisfy a single parity constraint. That's all, and the check node is doing decoding for that single parity code. Okay, right? So the difference between turbo code and LDPC codes is there you have several component codes. Okay, all of them are operating at the same time, and then you are doing message passing. Here you have only 2 component codes with long code words, you decode them and you pass messages. Okay, so in principle these two are roughly similar. I'll comment on this a little later also, but that's essentially the idea. Okay, anytime you have a code, okay, a long code which you cannot directly decode very optimally, what do you look for? You look for subcodes, smaller codes which have enough structure for which you have easy to implement optimal soft input, soft output decoders. Once you do that, you decode the subcodes, and then what do? You do message passing to improve the performance all around. Okay, that's the idea. Okay, convolutional code by itself is not good enough to get to capacity, but you have 2 together, and then they are operating in this message passing turbo fashion, then they can help each other out and get to capacity. Okay, so it's like 2 students, okay, who are not maybe the best students in class, but they keep solving problems and keep exchanging ideas, and eventually they become much better than even the one single best student in the class. Okay, so that's the idea. Does something like that happen here or not? I don't know. Maybe 2 students get together, you become the worst in class. Okay, so maybe that's something that you can also anticipate. But as long as you make sure you're passing extrinsic information, okay, what one doesn't know is what is being sent to the other. Okay, what that's okay. I didn't put it right. What you get is what is something that you don't know. Okay, some fresh information. As long as it's fresh, there's no problem. If you keep circulating the same old stuff, then you're going to go down only, right? So that's the key idea. Okay, so let me draw the structure. I'll draw how the decoder looks, and then you'll see how the message passing idea is going to work. But then I also have to address what the component decoder is. Okay, so I'll do that also. But before that, let me draw the overall structure of the decoder, and you'll see how the message passing idea is kind of inbuilt into the structure. So it's quite easy if you understand this principle. Okay, so I'm going to take the received vector y. Okay, I'm going to think of it as 2 different parts. Okay, so I have to write something here. So I'll write it as y. I'll put s here, okay, to denote it's the systematic vector, and then I have the y1 vector, which is the received values corresponding to the first parity, and then I have y2. Okay, so this is a bit different from what I had before. Okay, so when you transmit, maybe you transmit like this, okay, and then you can do a rearrangement. Okay, what is the rearrangement? Take all the systematic things together and put them together, because I am going to think of them as one block. Okay, you can do a rearrangement and think of it as y0, y1 all the way to yk minus 1, and then you have y10, y11 all the way up to y1 k minus 1, and y20 all the way up to y2 k minus 1. Of course, you also have the termination ones, which you have to use suitably. Okay, I am not showing how you split that. You can split it depending on how you want. So this guy I am going to call as y systematic. This one I am going to call as y1, okay, and this one I am going to call as y2. Okay, so that's the idea. So this is the received, y1 is the received vector corresponding to the first parity. This is y2 is for the second parity, and ys is the what's corresponding to the systematic or the message part. Okay, so that's what comes into my decoder. Okay, so what I do here is I have to do some kind of a split. Okay, so I'm going to split it into 2 parts. Okay, so let me draw this a little bit differently. Okay, so I'll keep it like this, and then let me say, okay, so let me draw the decoder and then we'll see what happens. Okay, so I have BCJR1 and then I have BCJR2. Let me see if this picture is going to come out very nicely or not. Okay, BCJR1 and BCJR2. What is going to be input to BCJR1? YS and Y1. Okay, so that is what I want to be input to BCJR1. But let me be okay. So YS and Y1 is input to that. So let me write that down here. YS and Y1 is input to that, and it is going to put out output. So what will its output be? It will give me what will be LLRs for each of the message bits. Okay, so that is what it will give me. Okay. So likewise I can think of YS and Y2 going to the second BCJR decoder, and then that will give me once again LLRs for all the systematic bits, right, for the same set of bits. Okay. So you have to somehow figure out, okay, yeah, okay, so maybe you want to be very specific there. Okay, so I will say pi of YS. Okay, so it is saying, so because of the permutation, okay, so it is a permuted fashion list of that, but I guess it is, yeah, you have to account for it. Okay, of course you have to account for it because the sequence is different. Okay, all right. So that will give you a certain, okay, now it will give you again LLRs for each of the message bits, but in the permuted order. Okay, so what you have to do is somehow figure out what BCJR1 is producing, which is extrinsic to BCJR2. Okay, so you have to figure that out. I'll tell you how to figure that out. Okay, so that, let's say somehow you figure out. Okay, so you subtract, what you do is you subtract intrinsic information. Okay, so you will get the extrinsic information. What should I do to the extrinsic information? It should go to BCJR2. Okay, so this one should go to BCJR2. So how can I draw that? So let me see. It's going to get a bit messy, but yeah, I guess there's no way to avoid that. So let me do this. Okay, but when it goes here, maybe you want to put a permutation in there also. Okay, because it's in a permuted order. So maybe I want to say there's a permutation. So let's say I do a pi here, and then I give it to BCJR2. Okay, so this is basically extrinsic information. Okay, so I'll call it LE1, which is extrinsic information from extrinsic LLR from BCJR1. Okay, so of course BCJR2 now should be able to use the extrinsic LLR. Okay, I haven't told you how BCJR algorithm uses extrinsic LLR. We'll see that soon enough. It's not too difficult. We'll see that, but let's suppose that we can use the extrinsic information. Okay, if you can use the extrinsic information, then it will produce now some LLR which is going to be better than just BCJR2 working on by itself. Okay, so you first get YS and Y1 here, run BCJR1, you get some LLRs for each of your systematic message bits. You subtract the intrinsic component from that. Okay, so I'll tell you how to compute the intrinsic component soon enough, but right now we don't know how to subtract this. Then you get the extrinsic component, you permute it, and then feed the extrinsic information to BCJR2. Okay, the BCJR2 now uses pi of YS and Y2 and the extrinsic information, okay, to compute what? New LLRs for all the systematic bits. Okay, so you don't stop here. What you do next is, okay, you will again subtract what is, let's say, intrinsic, okay, and then you should also subtract the effect of LE1 also. Okay, so the effect of LE1 also should be subtracted. Okay, so you should not feed back that same information to the BCJR1. Okay, it gave you LE1, so you should not do that. Okay, you subtract intrinsic and then effect of LE1. Okay, so how do you do this? We don't know yet. We'll see that. Okay, and then what do you do? yeah, you have to do a pi inverse. Okay, so you know that this is something that has to be inverted, and then what do? You pass this back to. Okay, there is no easy way to draw this, so I will do this. Okay, and this will be LE2. Okay, and that is extrinsic to BCJR1. Okay, now what is BCJR1's job? It is going to use YS, Y1 and LE2 and produce even better LLRs for all the message bits, and then again you should subtract intrinsic and LE2. Okay, you should subtract both of those and then send it once again back here, okay, and then this repeats. Okay, so you have this turbo processing, so to speak, to get better and better LLRs for your message bits. Okay, this is a picture of the turbo decoder. Is that okay? It's not bad, it came out quite neat. Is that okay? So there are several questions. I mean, when do you stop, for instance? Yeah, I mean, so there are several rules you can use. Some people are suggesting that LLRs, once they become sufficiently high, they may not be all high. You know, some LLRs might refuse to become high. And what do you do? So, for instance, the usual rule that's used is after 5 times or 10 times you stop. So that's the most implementable rule, because that's what you can implement in a system. After so many iterations, after taking so many clocks, you have to stop and say what it is. Okay, so that's something you can do. Some people have some more clever ways of putting a CRC for their message and then figuring out if the CRC is satisfied for the decisions. Whenever the CRC is satisfied, you stop. Okay, CRC, by the way, is cyclic redundancy check for figuring out if there are errors in your bit packets or not. So those are things that you can try. Okay, so but usually a common rule that's used, at least in the standards, they don't provide for CRC in the message, maybe not. So then you have to use simply 5 or 10 iterations and stop. So usual number is 5 or 10. Okay, so an iteration consists of 2 different BCJRs. Okay, so you can think of the first half iteration and the next half iteration. You stop at any point. Okay, you stop either there or here. Okay, so that's it. That's what triggered the revolution. Okay. So it's a bit non-trivial why this works. You know, if you ask me the question, why does it work? Why is it that the individual codes are not that great? When I say not that great, they are not capacity approaching. They cannot get to the capacity. But somehow when you do this turbo idea, then it works well. Okay, things like they complement each other. I mean, I don't know. You can be happy with such answers. I mean, if you want more precise answers, okay, then what a marriage broker can give you. You know. So then you have to look for more governing principles. You know, I mean, what is the idea? Let me see. What do you think? Why is this suddenly all the way better? Randomness is better, is what you're saying. Okay. So first thing is, it's very implementable. Okay, so that's the first big idea. Okay, so the general rule that you can remember is anytime you have an implementable soft decoder, it's likely to be very good. Okay, so that's kind of something which is generally true. You know, I mean, the only problem with the achieving capacity is not being able to decode. Okay, people knew that any random code you pick is good enough. Okay, just construct your parity check matrix with putting random ones here and there, it's good enough. Okay, so it works. It's not, the code is good, but then what's the problem? I cannot decode it. Okay, I cannot do soft decoding. So that's roughly what's happening here. So you come up with a nice, clever, good soft decoder for your code, and that code is sufficiently random. Okay, that code cannot be one code like repetition code. Okay, then that's not going to be very good. Okay, so you have to have a sufficiently random code. So when I say sufficiently random, what do I mean? The code design method should be able to produce lot of codes. So how am I producing lot of codes? I have only 2 codes here, right? The trick is the interleaver, right? So every type of interleaver I have a different code. So when you are addressing a large space of codes like that, you are highly likely to find good code. So finding good codes is not a big deal. Okay, you might be able to find it quite easily. Okay, but then the problem is, how do you come up with a good soft decoder which is implementable and it's also good? I mean, it has to be a little bit good. It cannot be just like that. You can't take randomly some values. Okay, it has to be something meaningful. Okay, Once you put these things together, most things work out. Okay. So at this point, even today, people do not have a really good understanding, very clean understanding of why is it that this works. Okay. Also another thing I should point out is this works only for finite bit error rates, finite frame error rates, fine. Low but finite. Okay. So you can go down to 10 power minus 5, 10 power minus 3 frame error rate. You can't give guarantees that it will keep on going down. Okay. On the other hand, capacity is something which you can achieve with arbitrarily low frame error rate. So really it does not fully solve the problem, but in practice 10 power minus 3 frame error rate is more than good enough. I mean, nobody is going to do more than anything like that. Okay. And today anyway IP packets are bursty and all that, so you do not need to really guarantee very huge very low frame error rates except for things like storage, etc. Okay. For communications, frame error rate of 10 power minus 3 is good enough, and for those kind of frame error rates, it is enough if you apply these general principles. What are the general principles? Your code design should have a random element which makes sure that you are addressing a large space of codes. Now you are not stuck with just one code, you have to be able to address a large space of codes. And next, it should, in the decoding, you should be doing soft decoding, and you have to use the idea of message passing. Okay, the message passing seems like the really best idea for designing these good soft decoders. As long as you use principles of message passing. What is the most important principle in message passing? Extrinsic. Okay, so extrinsic is the most important principle. You should not keep sending information that your other component decoders already knew. Okay, then you are only increasing the instability in the whole process. So you make sure you're not making those mistakes, and you use message passing ideas, you're going to have a good implementable decoder. Okay, so once you do that, it works fine. Another common idea is this concatenation. Okay, the notion of looking at a long code word as a small part of a long code word being a separate code word by itself. Okay, it might be as simple as a parity check code, just one parity check, or it might be more elaborate like a convolutional code. Okay, but as long as you do that, you can have different component decoders, and then you connect them up, use principles of message passing, you are going to be fine. Okay, so maybe I should write down these principles. It's interesting to write down stuff as opposed to do derivations. Okay, the first idea is code needs to be random enough. Okay, so the reason why you want to have a random element is you want to address a large space of codes. Okay, of course this is not strictly necessary. Okay, if you find the best code, then you don't need any random element in it. You know that it works. There's no problem. Okay, but if you're not sure, just make sure that you address a large enough code so that any one code is good enough, and then you can work with it. Okay, so that's the idea in the code, and then in the decoder, you have to do soft message passing. Okay, so that's the main idea. Okay, and what enables soft message passing in the construction of the code? More than concatenation, I want to use the word decomposition. Okay, the code decomposition should be possible. This is again a crucial idea in the design of the code. Okay, what do I mean by decomposition? A loose word again, but you can decompose a large code word into several small code words. Okay, and these several small code words might even overlap. Okay, whenever they overlap, you have to make sure that in your message passing you take care of the intrinsic part. You remove the intrinsic part before you pass the extrinsic part. Okay, so once you do these things, you are fine. Okay, so this is the general. What are these ideas useful for? These ideas are useful for approaching capacity. At low finite SNRs, FERs. Okay, so this is important. This word is often not emphasized when people talk about low turbo codes and LDPC codes, because when industry is so excited about it, and in industry it's enough if you have low finite SNRs, FERs. Okay, so that's almost capacity approaching. But in theory, these are not capacity approaching. Okay, so it's not at capacity approaching. You cannot guarantee arbitrarily low FER set. Okay, so this is good enough in practice. Okay, anyway, so this has nothing to do with turbo codes by itself. This is just some general principles that maybe we have observed, or maybe I have observed and told you, or maybe both of us have observed together in these LDPC codes and turbo codes. Okay, in fact, these are not the only codes out there. Okay, there is something called a turbo product code, which is again a manifestation of this principle. And then there is something called repeat accumulate code, again a manifestation of these ideas. So many other ideas out there, okay, of constructing codes which have a random component, or maybe not even random component, codes that have good code decompositions. Okay, some code decompositions are there for which there are nice component decoders, and then you do message passing carefully and you get good performance. Okay, it goes down. When I say good performance, what I mean, low finite FERs are possible and at close to capacity. Okay, that's the idea. Okay, so the missing element in the turbo decoder is a BCJR for which can use extrinsic information, okay, and how to get rid of the intrinsic information and the effect of the extrinsic information that was input to the BCJR decoder in computing the extrinsic out. Okay, so how to use extrinsic input and how to compute extrinsic output. Okay, so that's the idea. That's the only thing that's missing here. So let's do that. BCJR with extrinsic input output. Okay, so remember, what is the extrinsic input? It's LLR. Okay, it's LE. It's interesting. Some people, I don't know, I mean, I find this fascinating. I mean, in any place you always have this, people come up with answers, immediate answers, which is just good. I mean, that's an important skill, believe me. So you have LLR for the message bits. Okay, so that is what is extrinsic information. Okay, what is extrinsic output again? Once again, LLRs for the message bits. Okay, now what is intrinsic? What am I saying is intrinsic to both the decoders? Okay, so I haven't defined it properly, but the way you have to think about it is the final total LLR that's computed here, okay, will have some component from LE2. It will also have some component from YS. Okay, now both these things are known to BCJR2. BCJR2 knows YS. It also knows LE2. Okay, so I have to subtract that component of this total LLR which came from LE2. Then I also have to subtract that component of the total LLR which came from YS. Okay, once I subtract those two, I will get definitely my extrinsic output. Okay, so that's the idea. Okay, so what we have to try to do is the total LLR that we computed in a particular stage. There is a formula we used for computing the total LLR. Can we split it into the LLR from the channel plus the extrinsic LLR plus the extrinsic LLR input plus something else? If we can split it like that, then what can you do? You can simply subtract these two things and you get the extrinsic. Okay, so that's the idea. So what we have to see is first how BCJR uses the extrinsic input. That's something we have to see. Next thing we have to see is how do you get rid of the effect of intrinsic information and the extrinsic input information. Okay, so for that, the trick is to decompose the total LLR as systematic component, intrinsic component plus the extrinsic input component plus the additional extrinsic output component. Okay, so that's what we do. Okay, so how are we going to use the extrinsic input? That's the first question. Okay, remember, if you look at the Lth stage, what are the various probabilities that we are trying to calculate in the Lth stage? There is alphas on this side, there are betas on this side, and these things have nothing to do with extrinsic or anything. Okay, everything is computed first using the branch metric. Okay, so branch metric is the important thing which you compute. After that, alphas and betas are purely functions of the branch metric. So if at all extrinsic input is going to be used, it should be used in the computation of branch metric. That's all. You cannot use anything else. Once the branch metrics are fixed, alphas and betas are simply functions of the branch metric. You can't do anything else in the alphas and betas. Okay, so only thing you have to do is in your branch metric you have to incorporate any possible extrinsic input. So how do you do that? So let's see how do you define the gammas? Gamma L S prime S, is that the notation that I used? Gamma L S prime S, what is the formula for this? It's P what? Okay, so we had a formula for this. It's S L plus 1 equals S comma RL given SL equals S prime. Okay, so this is our formula for gamma of s prime comma s, and then I did some simplification on this, and then we came up to one final version. We said p of u s prime s. You remember this simplification, and then p of r l given v, no, v s prime s. Did we not come to this simplification? Okay. So, this is the branch metric, and this part there is no role for any extrinsic information there. Okay. P of R L given the particular two outputs is computed using what you received in the channel. It's just a function, it's a normal PDF, you substitute it into that, this whatever you get, e power 1 by root 1 by 2 pi sigma square e power minus RL1 minus V1 squared plus RL2 minus V squared. There is nothing you can do there with the extrinsic information or anything else. Okay. The extrinsic information is telling you, right, something about the priors. Okay. So, we were saying this P of u s prime s is going to be half. Okay. We do not know if that bit is 0 or 1. If we do not know anything, we are going to say it is half. But if some extrinsic guy is telling you that, guess what, my extrinsic LLR is 10 plus 10, then what does it mean? This is much more probable to be 1. So, I cannot simply say P of u s prime s is half. Okay. I have to use the extrinsic information in this part. Okay. So, here is where you use extrinsic information. Okay. Does it seem simple enough? Okay. So, how do you compute the extrinsic information is the question. Okay. It is not too difficult, right. So, LLR is given to you. How do you compute the probability? You substitute it into the formula and eventually work with it. If you do enough algebra, you will get the probability, right. LLR is basically log of probability that the bit is 0 divided by probability that the bit is 1. If somebody gives you LLR, you can definitely find the probability. Okay. So, after all, the two probabilities add to 1, and then you have given the other formula, you use both of them together, you are going to get something. So, you do that and you compute this. Okay. So, in BPSK AWGN, it is possible to do some simplification here, and remember, when we actually do it, we will actually implement the BCGR algorithm. We are not going to be using this gamma, we are going to be doing log of this also. Okay. So, you can do some simplification in the computation, and that is something we are going to try and do now. Okay. There is about 2 minutes left. So, I think maybe this is a good point to stop. Okay. So, we will pick up from here in the next lecture. We will see how to simplify this computation a little bit and use the extrinsic information in the gamma, in the branch metric, and then when you compute the final expression, you will see that the final LLR, output LLR, will nicely split into extrinsic plus the intrinsic plus the extrinsic out. Okay. So, then you can compute what is happening. Okay. So, let us stop here.